right, so let's come down and let's look at our first reaction, which is the reaction of hydrogen halide with an alkene. So the way that you're going to see this reaction is you're going to see your alkene. So here we have our alkene plus a HX. It's usually chlorine, bromine, or iodine here. And here we see an H atom added and an X added. That's the observed reaction. So the mechanism actually is pretty straightforward. So let's take a look at what happens here. So the first thing that happens is, remember that this double bond is your nucleophile. So that means that that's where the electron arrow pushing is going to start. So we're going to come over here and we're going to grab a hold of H. So here we can make a note. We add H first. Now when we do that, a couple of things can happen. So we can come over here and we can do this. So let's take a look at option number 1. So option number 1 would give us this, which are CH3s up at the top and over on the side. Now H could add right here. So if it added right there, the end of that double bond would be a CH2. That would be a positive charge, okay? Option 2. So we come down here, come over. Option number 2 puts the H atom at the end, so that CH2 would grab the H, and that leaves a plus charge right there. Now we know something about stability of carbocations from looking at E1 and SN1 reactions. And this is a primary carbocation. This is a tertiary. Tertiary is much better. So this top pathway here, we can simply write no reaction. It's got too big of an activation energy to form that carbocation. This is a lower activation energy since it's more stable, so that's the reaction pathway that we're going to do. So step 1, step 2, bromide is now the nucleophile. It's going to come in and grab a hold of that. That looks a lot like the SN1 type reaction, right? So what we're going to end up getting here is 1, 2, 3, and our bromo group here. Now, this right here has the potential to be a stereocenter. It's not here, but it could be. And if so, then we form a mixture of stereoisomers. So if you just remember that mechanism, then you don't really need to memorize any of the other little things down below. So the stereochemistry, halide can attack from either lobe, right, of the p orbital, right, which leads to the formation of stereoisomers. So that's what we're talking about up here with stereochemistry. Right, so remember that as sp2, right, and that carbon's lobe is up and down. So that bromide can attack on the top, or, well, really, I should say, and the bottom. We'll do both. As far as regioselectivity, so that's where does the H go? So we saw only one of the products is formed, right? So regioisomer number 1 would give you this, right? Regioisomer number 2 would give you that. So to get this, you have to go through that top pathway, right? And that means that you would have to have formed that guy as your intermediate. Forming regioisomer number 2 goes through this, and that's the more stable intermediate. That's the isomer that's formed. So again, we know that kind of instinctively. Now, there's a rule that's associated with this. So it was a long time ago, about 150 years ago, this guy named Markovnikov, who's a Russian chemist, noticed that the H is generally placed at the double bond position already bearing a larger number of H atoms. And that led to a rule called Markovnikov's rule. So this one is a big deal guy that you need to know. Now, what I like to say sometimes here is that rich get richer. So the carbon with more H's gets more H's. Sometimes we would say gots more, gets more. Okay, so it's all based on the stability of that carbocation that forms there. So let's look at an example here together. So if we look at this problem right here, so this carbon double bond, remember, that's your nucleophile. And the first step of that reaction is that we're going to do this. Now we know from that Markovnikov rule, and also from the stability of our carbocations, right, that the H atom is going to go down here. Right? That carbon here has more H's, right? So it's going to get more H's. And what that leaves us with is the more stable carbocation. I tend to think of the carbocation stability rather than the rich get richer. But anyway, they lead to the same thing. All right, and then the second step of this would be bromide. And now remember that that atom is sp2, and that p orbital is coming out at us and going back. So if we come in and get the front p orbital lobe here, if we get the front lobe, then the bromide would be pointing at us and the methyl group would be pointing back. If we move around the back and get the back p lobe, then the bromide would attack from the back and the bromine would be on the dash there. So you get a mixture of stereoisomers. So quick question, what's the relationship between these two? Well, in this case, they're diastereomers of each other. Right. Notice also, it's an important point, somewhat obvious after you've done it a while though, is that that carbon atom that has a chiral center, that's not going to change at all. Okay. Now this whole idea of Markovnikovs, again, just as a reminder, is based on the principal idea that the first step of this reaction leads to a carbocation, and the carbocation that has the lowest activation energy will be the one that has the more product formed, I guess I should say. So over here, looking at this, H could go to that position, right, or to this position. So if it goes to the end, right here, then we get a secondary carbocation. Right? If it goes to this first carbon that has, right, fewer H's, then we come over here and we get a primary. And that primary has a larger activation energy, right? It goes all the way up to this. So that larger EA means a slower reaction for us. Okay? So if we can kind of remember those principles, it helps us explain actually a couple reactions in this chapter.